Example 4 and 4.5. For each of the following, choose a linearization with the center not at x equals a, but a nearby value, okay, a nearby a value at which the function and its derivative are easy to evaluate. State the linearization and the center that you're going to pick. So, as you can see, this is giving to you f of x equals third root of x, okay, and an a value that they pick is 8.5. There's no way that I can do a third root of 8.5 in my head right now, okay, and get a good answer. So it says here, pick a nearby value that is easy to calculate, okay. So my nearby value, class, it's going to be 8, okay, because I can do third root of 8. But first, it says I need to also do the derivative as well. So let's find the derivative first. F prime of x is 1/3 x to the negative 2/3, okay? So I'm going to, and if you want to, you don't have to. You can rewrite this as a radical. So it's easier for you to calculate if that's you. And again, you do not have to. So my nearby value, I can't spell near, can I? Nearby value. I want to pick a number or value that I can use third root in. So I'm going to say nearby value is 8. Yeah. Okay. So I'm going to evaluate this as x equals to 8. Okay. So let's plug it in. 1 divided by 3, third root of 8 squared, which is 1/3. I can take out 2 twice, so that's 4. So this is going to come out to be 1/12. So that's my nearby value, okay? But it also says choose the linearization. So what that means is I need to use my linearization graph. So L of x, remember this, equals f of a plus f prime of a times x minus a, okay? So I'm going to plug in 8, okay, for my f function, because that's the value I've chosen. Here's my f function. When I do f of my nearby value, which is 8, which is really third root of 8, which is 2. So my f of a is 2, okay? So this gets a 2. Then plus f prime at 8, I already found. This is right here, 1/12, plus 1/12. Then I need to go x minus 8, okay? So 8 is the nearby value that I have chosen. So let's make this prettier than what it is right now. So 2 distribute, so that's going to be 1/12x. When I distribute, that's negative 8/12. Simplify that, divide by top and bottom by 4. So that's going to be negative 2/3. Okay, combine 2 and negative 2/3. So my answer is going to be 1/12x. This is the linearization that's going to help me approximate my function. 1/12, and that's going to be 2. Convert that to 3 over, denominator is 3, so I will need to convert that into 6/3. So 6/3 minus 2/3, so that's going to be 4/3. So that's going to be the linearization approximation of my function. And that's exactly what you have to do. Okay, it says for each of the following, choose a linearization with the center not at x equals 8, but a nearby value. Okay, I don't want 8.5. I want a nearby value that's easy for me to calculate. Okay, and it says center. Say the center. I pick 8, so my center is 8. Perfect. Similarly to cosine, okay? Cosine, there's no way I can do cosine of 1.7. That is not going to happen in my brain. But would you agree that cosine, easier values to pick are 0, pi/2. These are nice ones. Even pi/3, pi/6, and so on, right? Things that you can calculate without a calculator. Well, pi/2, it's about 1.5-ish, okay? And so nearby there, that's what I'm going to pick. So center, which is AKA nearby point, is going to be pi/2 for me. So I'm going to box that up because it said state that. Okay. So I'm just now going to do the derivative. F prime of x equals derivative cosine of x is negative sine of x. Evaluate it at x equal to nearby point, which is your center, pi over 2. So that's going to be negative sine of pi over 2. Sine of pi over 2 is 1. That's going to be negative 1. So my slope is negative 1. In addition, my linearization, if I can say that quickly, I need to have f of a. So your f function is cosine. So f of pi over 2 is cosine of pi over 2, which is 0, which is okay, no big deal. Then now let's plug into my linearization function. So L of x equals f of a plus f prime of a times x minus a. This is my function. Okay. So L of x equals f of a is 0 plus f prime of a was negative 1 times x minus, sorry, my nearby point was pi over 2. Let's distribute. Okay. This is going to give me a negative x and a positive pi over 2. So this is as far as I can go in terms of my linear approximation function. With differential, let's define that really quickly. Let y equals to f of x be a differentiable function. Differentiable function. The differential dx is an independent variable. Okay, so differentials. So let y equal some unknown function. Let's call it f of x. Be a differentiable, oops, there's a missing L, function. The differential dx is an independent variable. The differential dy is dy equals f prime of x times dx. dy depends on both x and differential dx. Okay. So let's try exemplify and apply this rule. Example 5, for each of the following, find dy, and b, evaluate dy for the given value of x and dx. So example A, and I forgot to give you what x is. X is going to be at negative 2, and dx is given to you at 0.1. So let's find dy. Well, we do it normally. We already know how to find the derivative, dy over dx. Okay, so dy over dx is, let's use the quotient rule. That means u prime, that means on the top, u prime times v minus v prime times u all over 1 plus x squared. With that said, we are going to have 2 times 1 plus x squared minus, this is, oh, what is that? What did I write right there? This is supposed to be 1 plus. So the derivative of that is going to be 2x times 2x all over your denominator, which is 1 plus x squared. Let's keep on going. We are going to have 2 plus 2x squared minus 4x squared all over 1 plus x squared. That will keep on going to give me negative 2x squared plus 2 all over 1 plus x squared. Now, this equals, whoops, this equals dy over dx. Okay, I'm only interested in dy. See this right here? So all you have to do is multiply both sides by dx. It's that easy. So that means dy is negative 2x squared plus 2 all over 1 plus x squared, and then times dx. So that's what we box up for what part A has to be. That's part A. Voila! Okay? It's that easy. Now part B, we just have to plug in what x is and what dx is. So give me the change in y. dx is a small change in x, and dy is a small change in y. So let's plug it in, part B. B says, let's plug in negative 2 for x and 0.1 for dx. All right, slowly, let's go. dy is negative 2 times negative 2 squared, because that's what x is supposed to be, plus 2 all over 1 plus negative 2 squared, all of that square. Work that out first, and everything is going to be multiplied by 0.1, which is dx. Okay. Now, on the numerator, that will give us a negative 6 over, on the denominator, that will give us 25. All of that need to be multiplied by 0.1. So the change in y is a negative 0.024. So that is what dy is. dy is a small change in the negative direction. Okay? And that's what we were asked to do. It's not very difficult because we already know how to do all the derivatives already. Let's try it again with example 5b. And again, it looks like I forgot to give you what x values was supposed to be. X will be 0, and dx is going to be negative 0.2. Let's do dy dx, which is the derivative. dy over dx, I'm going to use product rule and chain rule. U prime is going to be 1, so now I have 1 minus x squared plus x times the derivative of that radical 1 minus x squared, so it's going to be half times 1 minus x squared to the negative half power. The chain rule says I need to multiply by the inner. Okay, all of that right there. Let's simplify that really quickly. From there, this becomes 1 minus x squared plus this right here, and that guy right there becomes a negative 1. So okay, let me fix this. So this looks like a negative half, but that's not supposed to be. It's supposed to be a negative 1/2 as an exponent. All right, so that's going to be negative x squared in the front, and then I'm going to write this as a square root of 1 minus x squared, like that. I would now find a common denominator, so that means 1 minus x squared all over common denominator of 1 minus x squared. Let's simplify that some more. This is negative 2x squared plus 1 all over square root of 1 minus x squared. So this is what my dy over dx equals. I'm not looking for dy over dx. I'm looking for dy equals. So we are now going to multiply both sides by dx to get rid of the denominator. Voila! Okay. So part A, answer dy equals negative 2x squared plus 1 all over square root of 1 minus x squared. And you can stick the dx back here. If you feel more comfortable, you can put quantity around the whole chunk. Either one, it's going to be just fine. We have one answer. Now we just have to plug in our values and find out what dy actually is when x is 0. So B, when x is 0, negative 2 times 0 plus 1 all over 1 minus 0 is 1 times negative 0.2. That will come out to be a negative 0.2 because 1 divided by 1. So right now, the change in x, when is a negative 0.2, at 0, the change in y is the same thing as the change in x. Differential estimate of change. Let's start with the definition, okay? Let f of x be differentiable, at x equals to a. Give me some space here to draw a picture of this, so don't write all there. the approximate change in the value of f, which is y, okay, when x changes from a to a plus dx is d of f equals to f prime of a times dx. So I'm going to give you two pictures. The first one, it's a difficult picture with all of the formal lettering and verbiage. And the second one, like a straight up simple example, okay? So this is the first one. Like I said, the first one's kind of difficult to understand, but that's okay. I'll give you another one soon. So let's pick A right here. Then I want to pick the change in A, so let's pick this spot. So A plus that dx. So you have two x locations. One is A, and then one is A plus dx. So if I pick A, then this value right here, well, let's label this. This is the x coordinate, and this is the y coordinate, which is also f of x, okay? So if I pick A, would you agree this blue distance that I just got done doing is the y value of A? So in theory, it's f of A, okay? So that's a y value. If I pick A plus dx, that space to the right, then this right here is the change in x, which is called dx, okay? Again, dx is the change in x. We also use linearization to approximate using line to approximate the value at A. So let's draw this really quickly. And this is a sketch, so don't hold me to my line. So this is my line, L, which is linear, oops, can't spell linear, linearization at A. Well, if you look at this, okay, so this is what it's saying. So we know dx is the change in x, okay? We picked A plus dx, which is this dot right here, is the, okay, it's all the way over here. Would you agree this is f over A plus dx? Okay, well, then what does that mean? That means this space right here, which is, by the way, the same as this space right here, okay, is the change in y, right? Which means the change in y, which means change in y, which is the same thing as saying the change in f, since it's f of x, okay, the change in f of x. Well, the change in y is y2 minus y1. Well, y2 is f of a plus dx minus f of a. This right here is the actual change of y, okay? Well, what is the approximation then? That's what it's really, this whole definition is about. Well, then what is really the approximate change value of y? Well, then it's really this piece right here, which I'm going to use red, okay? This piece, from here to here, okay? That right there is the approximation, it's a change, okay? And, well, that's the difference in linearization. Well, by definition, it's f prime of a times dx, which is a change in x, which, as you know, that is the approximation change in y, okay, from a to a plus dx. So this is what they're really saying. That right there is what they're saying. Now I'm going to draw another picture, which is a little bit simpler, so we can get a better understanding, like a line, okay? I'm going to give you an equation of a line. Super easy. I'm going to make some tick marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And let's start with, let's just give us y equals 2x. This is a made-up line, okay? No big deal. start at 0, go up 2 over 1, up 2 over 1. Here's our made up line. And again, this is completely made up, so we have a better understanding of this. Then let's go and pick A right here. This is A. And our next tick mark is A plus dx. Would you agree? Okay, A plus dx, because I picked A as 1, A plus dx is right here. So this is the change in dx. So dx right now, dx is 1 unit. Well, I can't have s. 1 unit. So what is the approximation for the change in y? Well, based on the formula, the approximation for change in y, which is this formula they gave us, is the first derivative of at a. So if I gave you y equals 2x, y prime is 2, times the change in dx, the change in x, which is dx, which is 1. So the approximation of the change in y, if I were to go from a to a plus dx, is 2 units. Should be 2 units, okay? Well, is that true? Is this 2 units? Sure it is. So that's what it's really saying. If it's a curvature, we are using derivative to approximate. So it's not always the actual. It's not always the exact. But it's good enough for us because it's easier to approximate, okay? So that's what this theorem is really saying. Well, let's use it right away to apply to example 6. For each of the following, the function f changes value when x changes from a to a plus bx. I believe that's really needed to be fixed to dx. Find, part A, the absolute change, okay, which is the actual change. Then B, estimate the change. What this question is really doing is, do you see much difference? Okay, is it that much of a difference? That's what it's saying. And C, approximate the error. That means you need to subtract the actual and the approximation. So part A, we want to find the actual change, the absolute change. So actual change is the y2 minus y1. Okay, in this case, it's f of a plus dx minus f of a. And they gave you a is 1, dx is 0.1 minus f of 1. So this is really f of 1.1 minus f of 1. And then we just have to plug it in. So first bracket, ready. 1.1 to the third minus 1.1. Close that up, take away 1 to the third minus 1. This is going to give me 1.3. Oops, that doesn't look like anything. This is going to give me equals 1.331. Take away 1.1. Box that up, minus 0. So that's going to give me 0.231. So that is my actual change. Then B, use our approximated change formula, which is the change in y. It's the first derivative at a times the change in x. Well, let's do first derivative then. The first derivative is going to be 3 y prime is equals to 3x squared minus 1. Then your x is evaluated at 1. So this is going to come out to be 3 times 1 minus 1, which is going to be 2. So df is 2 times 0.1, which is dx. Remember, dx is given to you right here. So that will give me a 0.2. So the approximated formula is 0.2, and the actual change is really 0.231. As you can see, it's a small gap. Okay, so that's what part C is asking. Find the error, which is an absolute value. So you're going to take 0.231 minus 0.2. This will give you a change of 0.31. That's not that big of a difference in terms of the actual and the approximation. Okay, let's try this one. Is this one going to give us a bigger error or a smaller error? So again, same thing. We want to find the actual change first, which is y of 2 minus y of 1, or y of x2 minus y of x1. Okay, for this one, f of a is 1 plus 0.01 minus f of 1. Let's plug it in. Well, let's simplify that. F of 1.01 minus f of 1. So here we go. 01 to the fourth minus 1 to the fourth. This is going to give me 0.0406. Even though I didn't tell you how to round, it's such a small number. When it's a small number, you want to carry out enough so we can understand the difference. Then B, it's the approximate change, which the formula says f of x is the first derivative at a times the change in x. So let's do the first derivative. F prime of x is 4x to the third. I need to evaluate it when a is at 1, so this is going to be 4. So d of f equals 4 times the change in x, which is 0.01. This is going to give me the answer of 0.04. Okay, so an error analysis tells me that absolute value of 0.0406, take away 0.04, this is going to give me a change, a very small difference between an actual y change from a to a plus dx to the approximation. Okay, so it's a very, very small change, which is good. The smaller the error, then the better it is for the approximated formula. Absolute, relative, and percent change. As we move from A to a nearby point called A plus gx, we can describe the change in f in 3 ways. Okay, so we have absolute change, so true and estimated. True means actual. So the actual change is going to be f of a plus dx, take away f of a, as we know. And the estimated is d of f equals first derivative at a times the change at a, that's an a, times the change in x, which is dx. Next one is the relative change. Relative change is pretty much talking about comparing two quantities. Okay. So for the true, we have the change in f divided by f of a. Over here, we have df divided by f of a. Then percentage, that's normal. We multiply everything by 100. So the change in f divided by f of a, and then times that to 100. Same thing over here, d of f over f of a times 100 if you want to know the percentage. Okay. All right, let's see what that is going to be used for. Example 7a. The radius of a circle is increased from 2 to a small increase of 2.02 meters. Part A, estimate the resulting change in the area. Estimate as a percentage of the circle's original area, which is good to know, right? If you move the radius 0.02 of a meter, I would like to know the actual number and what percentage is that, okay? So first, we might want to find the area. area equals pi r squared, and I'm going to rewrite this as a of r because I want to find the derivative with respect to r, which, as you know, is really dA over dr. Okay, dr is the change in radius, dA is the change in area. If you know those values, you know those meaning, then it's easy for us to find the change in area, which is dA. All right, so derivative says power rule, drop down to 2 times pi times r, voila. Then I would like to solve for dA, which means I need to multiply both sides by dr. Would you agree? So dA equals 2 pi r dr. Okay. Since they gave you radius is 2, we know the change in radius was 0.02. We can totally plug that in. So dA equals 2 pi times 2 times 0.02. We will crunch out that number, which is 0.08 pi, which is about 0.2513. I would take this exact, or I would take the approximation. Okay. I can write a complete sentence in all of that in just in a little bit, but right now let's just work out the numbers. At the end, I'm going to write a complete sentence for both parts. B estimate as a percent of the circle's original area. So that means percentage means d of f over f of a, and then I'm going to multiply by 100. Well, I don't have f, I don't have d of f, but I do have d of a, right? Because r is talking about area, d of area, over, I don't have f of a, but I have the area, the change in the area, and area of r, okay? Remember, r was originally starting out as 2, okay? So if we do that and we multiply by 100, we're good. The change in area, we found, I'm going to use the exact value, which is over here, of 0.08 pi. A of r, which is really what am I doing? Why is it moving like that? A of 2, maybe I'm just hitting something wrong. Okay. A of 2, which is 0.08 pi divided by, if I plug in 2 square, because pi r square is my formula, whoops, times pi, something is glitchy here with my computer, times pi, that will help me reduce the pi. So I'm going to have 0.08, over 4, and I do need to multiply by 100 to get a percentage that comes out to be 2%. Okay, I get the number for both parts A and B, so let's just go ahead and write a complete sentence. Okay, ready? Part A said estimate the resulting change in area. So the estimated change in area is about, you can write it as 0.08 pi or 0.25113, and then we can add the percentage in, okay? The estimated change in area is 0.2513 meter square, and that's about, we said 2% of the original area, okay? Box it up. There you go. So as you can see, the change doesn't look like it's a big number, 0.2513. So as you can see, is 2% of your total original area. Okay, let's do 7b. The radius of a circle is increased from 10 to 10.1 meters. Same thing, estimate the resulting change in area. If you went from 10 to an increase of 0.1 meter, what would be the area? And then tell me the percentage as well. Same thing, we're going to work out the same way. Area equals pi r squared, which I want to write it in terms of r, so I have a better understanding of what dA over dr means. So take the derivative, multiply both sides by dr, so dA equals 2 pi r dr. Your radius is 10, so I'm going to put in 10 for the radius, and dr is going to be 0.1, so dA equals 2 pi times 10 times 0.1. That will shoot out to be just 2 pi. And again, I'm going to write a complete sentence for both parts later, but let me just do the math first, okay? Part B. Let's figure out what percentage that is in comparison to its original area. So we are going to do dF over dA based on your formula times 100. I don't have dF though, I do have A because that's the area over A of R. Okay. Well, dA, we already found it. It is right there. We can just plug it back in. So that's going to be 2 pi. A of area started at 10, so I need to find out what that is. So 2 pi all over pi r squared, so 10 squared times pi. Cancel out the pi, so that's 2 over 100. So I'm going to multiply by 100. So, oh, it's 2% again. Okay. So here we go. The area, as you can see, final complete sentence. The area, as you can see, the dA changes to 2 pi. So area will have an increase, right? Increase of 2 pi meters square, and that's about 2% increase from the original circle's area. So that's about 2% increase comparing to the original's area. Comparing to the original area. Okay, original circle area. All right, guys, example 8 says, write a differential formula that estimates the given change in volume or the change in surface area. A, the change in surface area, so that's what we're trying to find. S equals 4 pi r squared of a sphere when the radius goes from A to A plus dr. So immediately, students, we can take the derivative, ds with respect to dr equals 8 pi r, okay? Now we can cross multiply just so we can have ds equals 8 pi r times dr. Well, in this question, it says, okay, well, give me a formula when it goes from A to A plus dr. Well, when radius, okay, changes from A to A plus dr. Well, you guys, the formula has radius in there. Oops, we're forgetting an E. Well, radius is now can be substituted with A. So if that is the case, this is now ds equals 8 pi times A and then times dr. And that's as far as we can go. So ds, students, is the change in surface area. Okay, and box that up. All right, let's try B. The change in surface area, S equals 6x squared over cube, when the edge length change from a to a plus dx. So similarly, let's do ds with respect to x. So you guys are going to have 12x. Well, we can solve for ds immediately by, we can now have 12x times dx, right? Well, students, it wants us to substitute a from a to a plus dx. So if we were to, oh, not that one, sorry, this one. If we were to take out x and put in a, we would have ds equals 12a times dx. And that's all we got to do here. Okay, guys, so now we're going to use the application, okay? So we're kind of incorporating example 8 with this. So 9a says the edge of a cube is measured as 10 centimeters with an error of 1%. The cube's volume is to be calculated from this measurement. Estimate the percentage error in the volume calculation. So let's use a variable. So let x be one side of a cube. In this problem, one side is measured with 10 centimeters. Well, let's find the volume. So volume with respect to x of a cube is x to the third, because it's length times width times height. Since the cube, all sides are the same. Well, let's find the derivative with respect to x. So this is the change in volume with the change in the one side. So this is 3x squared. dv represents just the change in volume, so we're going to cross multiply. So now we have 3x squared times dx. This is the change in volume with respect to x, okay? Well, since x is 10, and remember, it says here the measurement has a 1% error. Well, that means the change in x, which is the change in the measurement of one side, is going to be 1% of x. Well, 1% is 0.01 times 10. So as you can see, the measurement has an error of a 0.1 of a centimeter. So since our volume is x to the third, which has a volume of 10 to the third, which has a volume of 1,000 centimeters cubed, the change in volume that has the error is going to be 3 times, well, this is what I'm using right here, guys. 3 times x is 10, so that's square. dx we calculated from here, so that's going to get multiplied to here. So that's all of this is going to give me 30 centimeters cubic. Okay, so the change in volume is 30 centimeters cubic, but this one says estimate the percentage error. Now, if you look back at your notes, I gave you guys a formula. The percentage, okay, the estimated formula, I gave you percent change in your formula is df over dA. Okay, now, and then times it by 100. Well, we don't have f or dA, we have dv, okay, with respect to f of a, which is your volume. So the change in volume, this is dA, I think in your formula, this is going to be a parentheses, over volume of 10. So the change in volume divided by the volume when the side is 10, and then times 100 because it's going to be percentage. Well, we have dv, which we calculated as this. So dv is 30, volume is this, so that's 1,000, and we have to multiply by 100 because we want percentage. So student, this comes out to be 3%. Okay, so the estimated percentage of error for the volume is 3%. All right, B said, suppose the Earth were a perfect sphere and we determined its radius to be 3,959 miles. So 3,959 miles with an error of 0.1 of a mile. The Earth's surface area is to be calculated from this measurement. Estimate the percentage error in the surface area calculation. And obviously, guys, you know, I love application, and this is as real as it's gonna get, right? So anytime you guys we, human, do anything, there's always going to be some sort of an error in calculation or an error in measurement, or just could be called a human error. So here we go. So let's start with the surface area, which is S, which is going to be 4 pi r squared for a sphere. Then we are going to try to do the derivative, okay, the change in surface with the change in radius, 8 pi times r, and if we just want the change in surface all by itself, we multiply dr to both sides, so 8 pi times r times dr. Okay, so that is that for now. Well, let's go back and check really quickly. You guys, it says we have an error of 0.1 of a mile. So dr is the change, right, in the radius. And the radius is going to be 3959 miles. So the change in surface area, we're going to use this formula, which is 8 times pi. Radius is 3959. The change in radius is 0.1. We are going to bust out my calculator. Okay, this is going to give me 9950, and then surface area, so miles square. Okay. Now it wants us again to estimate the percentage, and again we are going to use the same formula from your notes, which is df over f of a, because it wants a percentage, so we will multiply this by 100. We don't have f or f of a, we do have the change in surface area with the surface area when the radius is 3959, and again multiply by 100 to get percentage. We calculated ds already, which is this number. So that's going to be 9950. Let's see, when we want to plug in s of the radius of 39, so that's going to be this formula. So hold on tight, okay? 4 times pi, 3959 square. And I'm definitely going to need a calculator. I need to multiply by 100. So with my calculator, it's going to be super tiny because you got 3959 square in the bottom. 0.00505%. So the change is really, really small. All right, guys. So that's it. Example 10 from 4.5. Estimate the volume of material in a cylindrical shell with the shell thickness being 0.5. Let's correct that to feet since these all measure in feet, okay? So with the thickness of the shell of a 0.5 or half of a foot. So what we know is based on the picture, we know the height, okay, is 21 feet. We are given the diameter is 10 feet, which tells me the radius is going to be 5 feet. The shell thickness, as you can see, this one's just shell thickness of half a foot. So that's really the change in radius is going to be 0.5 of a foot. Okay, so half of a foot. So if you see the thickness of it, so what's happening is the shell thickness is really what's happening here, right? So this is the shell, and that's going to be half of a foot. So that's the change in derivative. So question A says, estimate the volume. Well, what we want to do is write the volume formula down. Volume equals to pi r squared times h. The height is fixed because it gave us the height of 21 feet. Okay. So next step we want to do is we want to find the change in volume with respect to the variable, which is r, since the height is fixed. So what that's going to do is we want to do the derivative, 2 pi r times h. Well, we have to, this is estimate the volume. So we from here going to just solve for d of v, which is 2 pi r times h times dr. Well, let's plug all the stuff that we have in. 2 pi, radius, we know is 5. The height is fixed as 21, and dr is 0.5. If you don't have a calculator, I will always take the exact answer, which is 105 pi feet cubic, okay? Now, if you have a calculator and you want to punch that out, I'm okay with that too. It's 329.9 cubic feet. So I will accept either answer. So these type of questions, what you really want to know is, okay, they give all of these numbers are given to me. Do I know what they represent? Okay, so that's really what you want to be mindful of. So here's B. Estimate the volume of material in a cylindrical shell with the shell thickness now being 1 inch, and they give you a new height, a new shape. The new height is 30 inches, and the radius is 6 inches. So same thing, it says estimate the volume. So the first thing you want to do is write down the volume formula. Volume is pi r squared times h. And it says estimate the volume. That means you're going to have to find the change in volume. So we want to do the derivative of volume with respect to radius. Remember, since height is given to us, the height is a fixed value. So we don't have to worry about the height. So similarly, the derivative is 2 pi r times h. Then because it says estimate the volume, we are going to solve for dV. So that's 2 pi times r times h times dr. Let's plug in everything we have. So dV is 2 pi, radius is given to you as 6 inches. Then the height is given to you as 30. The change in dr, which is the thickness of the shell, is 1. So if you don't have a calculator, I would just take it as 360 pi inches cubic and leave it just like that. It's just fine. Okay, and that's as easy as it is to find the change in volume. The height and the radius of a right circular cylinder are equal. So the cylinder's volume, is given to us as pi times h to the cube. The volume is to be calculated with an error of no more. Whoa, that's my phone. Ha! That's my favorite song. Okay. Of no more than 1% of its true value. So let's spell that out. An error, okay, so the volume is to be calculated with an error of no more than 1% of the true value. Find approximately the greatest error that can be tolerated in the measure of h, and give it to me as a percentage. So earlier, as you remember, we were looking for the percentage of the change in radius, or we were looking for dr, or we were looking for ds, or dx, because it was the change on the side if we're talking about a cube. Now we're kind of going backwards. I'm giving you the change in the volume, which means that's ds, okay? The change in volume, it says here. But remember that when you are talking about error, it can be bigger or it can be smaller. So we are going to talk about an absolute value. The change in the volume cannot be more than 1% of the true value. True value of what? True value of the volume, obviously, because we're talking about the volume. So if it's talking about no more than 1%, so technically I can have 1%, just not more than that. So that's why it's an equal sign there. So guess what? We're going to have to find the derivative. So let's use your volume equation. Find ds with respect to h. So that's going to be 3 pi h squared. Let's find ds. ds is 3 pi h squared times dh. That's what ds is. Now we're going to take it and we're going to plug it in here. Well, ds, I know ds. ds, let's substitute it in. And remember, I'm using an absolute value, meaning that the change can go either way, in the positive direction or the negative direction. So 3 pi h squared dh is less than or equal to 1%. Let's convert that to decimal. So 0.01 times the volume. We have volume. Yes, ma'am. Volume, oh, that's super fat. Volume is pi h cubed. Okay, so that's the volume. So now let's do basic math. As you know, we are trying to solve for dh, so I have to get it by itself. Now, just because I'm putting an absolute value around it, because the reason the absolute value is around it is because to represent the change can be in the negative or positive direction. Now, when you're solving for it, you don't need to worry about it. We're just going to divide both sides by 3 pi h squared. 3 pi h squared. Cancel, cancel. So dh, okay, it's going to be an absolute value just because the change, again, can be in positive or negative direction. Let's see what happens. Over here, what's happening? The h squared is going to cancel with the h squared. The pi is going to cancel with the pi. Oh, nice. I'm sorry, there's one h left. I should say that. So now I have no more than 0.01 h divided by 3. Let's multiply it by 100 to get rid of decimals, okay? So we have dh, absolute value of dh, is less than or equal to 1h over 300. I can work with that. So, as you can see, I just now need to find the percentage. To find the percentage, I just have to multiply by 100. So if I multiply by 100, the change in h cannot be, cancel out the zeros, so 1/3 of a percent of h. And what is h? H is the height, okay? So now let's spell that out. We are going to say the height should be measure with an error, which is, remember, dh is the error for height, of no more than 1/3 of a percent. Okay, so that's what all of that is. I spell that out in verbals, that way we know what I'm talking about. This is 1/3 percent. There's an h, that means it's all of the height. So math and English, okay, whenever you are interpreting it, that's what it means. Last problem of chapter 4. Okay. The surface area of the sphere is to be calculated with an error of no more than 1% of its true value. Again, this darn no more 1%. So I would need a surface area. And so that means surface area of the sphere is going to be 4 pi r squared. I'm probably going to need to do the derivative with respect to r. So let's take care of it. That's 8 pi times r. Let's solve for let's solve for ds. So ds equals 8 pi r dr. All right, let's leave it alone. Okay, so an error of no more than 1% of its true value. That means your change in surface area is no more than 1% of the surface area. That's what it means, right? So let's figure it out. ds is this guy. Let's plug it in. Absolute value 8 pi r dr less than or equal to 0.01. Surface area, it's right there. Let's plug that in. 4 pi r squared. Let's solve for dr. Divide both sides by 8 pi r. Divide both sides by 8 pi r. With that, we can cancel out that and that. We currently have dr left by itself. Let's cancel some things on this side. Let's see. I have 1 r left on the top. A pi and the pi will be gone. A 4 and the 8 will give me 2. So that will leave me 0.01 over 2 of the radius. Let's multiply this so I can get rid of fractions. I normally don't like, not fractions, decimals. I don't like having decimals and fraction all together. So multiply the top by 100. That means multiply the bottom by 100, just so that way I can have the fractions all by itself. So no more than 1 over 200 over the radius. Okay, that's what multiplication is for, the radius. But it wants it in percentage. So that's just really going to multiply this by 100. So with that, dr is going to be no more than, cancel the zeros, half of a percent. and then because of r of the actual radius of radius. Okay, so how do we spell all of that out? The radius should be, not should me, should be measure with an error, which is, remember, dr should be measured, the radius should be measured with an error of no more than 0.5%, or you can even write 0.5%, or you can write 0.5% of the actual value of the radius. Okay, and that's sort of, you can probably write a better interpretation than that, but that's pretty much what it's about. So as you can see, this one, I gave you the percentage of error in either ds or dv, or sometimes if I give you area, then it'll be dA, and you're going backward to find either dr or dh, which is the height, right, the change in the height, or sometimes a side if it's talking about a cube. Remember earlier in the early examples, we've went and go the other route, so make sure you know how to do all of them. And that's it. It's an egg roll.